Thank you, Brilliant, for sponsoring this video. This is the Heisenberg's uncertainty principle, at least a version of it. Not only does it make the atom stable, but it allows you and me to exist. But wait a second, what exactly does it say? Well, here's how my teacher explained it to me. If you look at this photo taken by a high-speed camera of a moving tennis ball, you know exactly its location. But do you know where it's going? I'm like, no, it's a photo. So it could be going in any direction. I have no idea, meaning I have no clue about its velocity. But what if I took a long exposure photo of that same tennis ball? Ooh, now I know it's going in this direction. And by looking at the blur, I can estimate its speed as well, which means now I have a much better estimate of the velocity. But notice, now I don't know where the location of the ball. I don't know where the ball is, so I've lost the location information of that ball. In other words, if the uncertainty in finding the location of an object is very tiny, then the uncertainty in finding the momentum of the object, because the momentum is given by its velocity, that is very large. But if you know the velocity or the momentum very nicely, its uncertainty is very small, then there will be huge uncertainty in the position of the ball. And guess what? Elementary particles like electrons behave in a similar way. If you find its position exactly, you wouldn't know where it's going. You wouldn't know anything about its momentum. On the other hand, if you find its momentum exactly, you wouldn't know anything about its position. If you take the uncertainty in the position and the momentum together, they must have a minimum value. And that minimum value happens to be h divided by 4 pi, which is the uncertainty principle. Now, for a long time, I thought that this makes so much sense, like so much intuitive sense. But then I realized there's a problem with the analogy. You see, if you go back to that photo, I can actually figure out the velocity of the ball over here. You know how? Instead of using a still camera, I use a high-speed video camera. And then I just look at the next frame, and by looking at the next frame, I will know which direction the ball is going, and I can figure out this distance and calculate the velocity. Higher the frame rate, better my calculation. So this is just a technological limitation. I can figure out the velocity, but Heisenberg's uncertainty principle, it is not a technological limitation. Another explanation I heard was that, hey, if you try to figure out where the electron is, you have to bounce off light on it. And when you do that, you're going to disturb the electron, disturbing its momentum. And that's why you will have no idea about its momentum when you learn about its position. But again, the problem is the uncertainty principle has nothing to do with measurement. It is much more subtle. So for a long time, I thought I will never get a rigorous intuition behind what's really going on over there. That is until I read Feynman lectures, and then my mind was truly blown. So the hope of this video, if I do it right, is not just to understand the principle, but to actually rediscover it intuitively so that we'll understand it in our bones and guts and it'll make perfect sense. And I think Feynman helped me do that, so I'm sharing it with you. So if you're ready for this, let's begin. So where do we start? Feynman says we need to first understand the idea of wave-particle duality. And I'm like, wait a second, I know what that means, right? I mean, electrons, for example, are both waves and particles at the same time, right? And Feynman says, no, not quite. I mean, what do you mean? Well, Feynman asks, Mahesh, if you have an animal that flies like a pigeon, but also has a face like that of a mouse and the fur that of a mouse, would we say that animal is both a pigeon and a mouse at the same time? No, it's not. It's a different animal altogether. It just shares some common properties with these two, but it's a different animal altogether, right? Similarly, an electron has certain properties that are similar to that of the traditional particles. For example, they come in lumps, he says. So you will always find an electron in one particular location. You can count 1 electron, 2 electron, 3 electron. They're not spread out or anything like that, okay? Which is very similar to how particles are. They come in lumps, like the grains of sand or a tennis ball or other things like that. But the electrons are not particles. Why? Because they do certain things that normal particles don't do. For example, if you were to set up an experiment with the 2 holes, which is the double-slit experiment, and shoot electrons through them, you will get something which you wouldn't expect from grains of sand or tennis ball. You'll get a pattern that looks like this. Think about it. How does that make any sense? Normal particles don't do that. Therefore, electrons are not normal particles. But this pattern is an interference pattern that you get from waves. And therefore, this means electrons also have properties like they interfere, they diffract, properties that we associate with traditional waves. But does that mean they're waves? No, because remember, waves do not come in lumps. They are continuous. They are at multiple locations at the same time. But electrons come in lumps, which means they're neither waves nor particles. They're their own things. Feynman says they act screwy in their own way, which sounds disappointing, right? But here's the good news. Electrons are screwy just like how protons, neutrons, or even photons and other things are. They're all screwy in the same way. So the physics for them is pretty much the same. We call them quantum objects. So they are neither particles nor waves. They share certain properties with particles or waves, but they're neither of them. This is the whole idea behind the wave-particle duality. Okay, so since Heisenberg's uncertainty principle applies to quantum objects, our next question would be, how do we deal with the momentum and the position of quantum objects? So let's start with the momentum. Feynman asks, Mahesh, do you want just a formula to calculate momentum of such quantum objects, or do you want some intuition behind it? I'm like, of course, give me the intuition, right? So for that, Feynman says, let's go back in time a little bit. Around 1900s, where we thought we understood what light was. We celebrated, thinking that light is an electromagnetic wave. We understand optics is solved, almost all the physics is solved, nothing else remains to do. Only to realize a little bit later that there were certain experiments like the photoelectric effect or the black body radiation, where we couldn't explain what was going on using the wave theory. This is where folks like Max Planck and Albert Einstein came along, and they realized that light must be coming in chunks as well, must be coming in lumps as well. The quantum nature of light was discovered by these folks because of these experiments. This is your photons, and the energy of the photons, they hypothesized, has to be given by this particular equation. E is equal to h nu, where E is the energy of the photon, h is the Planck's constant, and nu represents the frequency of light. Well, earlier it was just a hypothesis, but then experiments like photoelectric effect actually confirmed that this must be true, okay? Now, at this point, Feynman asks, Mahesh, do you see something interesting over here? And I'm like, no, this is a usual equation. I know about it. What would I see? Feynman says, if you were de Broglie, okay, or de Broglie, however you want to call him, okay, then you would notice that, hey, nu is the frequency, right? Frequency of any wave is given as c divided by lambda. And I'm like, yeah, so what? Well, now if you bring the c on the other side, you get e divided by c on the left-hand side. And I'm like, yeah, so what? Well, from the classical electromagnetic wave theory, the momentum of an electromagnetic wave is given by E equals C. Sorry, E divided by C. Do you remember this, Mahesh? I'm like, yeah, I kind of remember this. We did a video on it, a video where we showed why light has momentum even without mass. We showed that the light's momentum comes from its energy. You don't have to watch that video. I'm not fishing for views, but we derived it intuitively over there, so you can check it out if you need to do that. But this comes from classical physics, okay? But anyways, de Broglie, what he says, what he looks at it and says that, hey, that means I now understand that the momentum of these quantum light particles, whatever you want to call them, that should equal the Planck's constant divided by the wavelength. I have an expression that connects the momentum and the wavelength. Why he got excited was because he said, look, if light, which we thought was a wave, happens to have particle properties, maybe particles like electrons, which we thought to be particles, may also have wave properties and might also have wavelength associated with it. So maybe this equation also works for electrons. That was the hypothesis that de Broglie put forward. Again, back then it was a hypothesis, but today we have verified it, that this is true. So this works not only for photons, but all quantum objects. And that means if you want to find the momentum of any of these, like say electrons, this is how you find it. You take the Planck's constant and divide by the wavelength, and that's how you calculate the momentum of the object. And at this point, Feynman is like, Mahesh, you could have put in some simulations over here to get the point across better, right? And I'm like, yeah, I could have, but I don't need to, because you can find those simulations at brilliant.org, the sponsor of this video. I love Brilliant mainly because just like what we're doing over here, you get to rediscover ideas intuitively in subjects like math, data, programming, and even AI. And I've been recommending Brilliant to even my students way before they started sponsoring me, mainly because instead of just watching the videos passively, you get to actively interact with it. So even with about 15 to 20 minutes a day, because you're doing active learning, you'll start gaining problem-solving skills. Take their course on quantum mechanics, for example. You immediately start interacting with waves to understand superposition, start making predictions for the single-slit experiments, and understand all about wave-particle duality. And yeah, that's just the first chapter. I mean, there's so much more lined up over there. And if you think this is cool, then what's even better is you can try everything Brilliant has to offer for free for a full 30 days by just going to brilliant.org/FloatHeadPhysics. And of course, you will also get a 20% off on the annual premium subscription if you decide to buy it. The link is also in the description. All right, Heisenberg is waiting for us. So this is how we think about momentum for quantum objects. But now comes the last question. How do we think about position for the quantum objects? That's the last piece of the puzzle. And for that, Feynman says, again, we have to go back in time a little bit, okay? Once we put forward this hypothesis that these electrons, for example, can have wavelength, a question was asked. If electrons have wavelength, they should also have a wave equation, right? Where's the wave equation? And that's where Irving Schrödinger says, hold my cat. He comes back in a year with the wave equation, which we call today the Schrödinger's wave equation. This equation looks scary, and maybe it's a topic for a future video, but what's important is that it encapsulates all the properties of these quantum objects. Actually, not all. Some properties like spin was not captured very well. Anyways, then comes the big question, what does that equation even mean? I mean, think about it. If you solve this wave equation and you get a wave, say, that looks like this for an electron, what does that wave represent, right? Because it's not the electrons are wiggling up and down. No. This itself is the electron. Then what do these peaks and valleys even mean? That was the big question. Well, we call these peaks and valleys, the symbol that we use to represent the peaks and valleys is psi. And we realize that maybe psi doesn't, the peaks and the valleys don't really mean anything. But we also realize that if you take a square of these peaks and valleys, then that gives you the probability of finding the quantum object at that particular location. And I'm like, what does that mean? What do you mean, Feynman? Okay, Feynman says, Mahesh, look at these locations. Okay, what's the value of psi over here? The amplitude, it's 0. This means the probability of finding the electrons over here is 0. So if you were to shine light on this electron to try and locate it, there's no chance that you would find the electrons in these locations. On the other hand, look at these locations. The psi value is very high. So the probability of finding the electron over there is very high. So if you were to shine light on this electron, there's a very good chance you'll find the electrons over here. And this is the coolest, weirdest thing about quantum objects. They don't really have a position until you measure it. It's not like you don't know where the position is. No. We know that the position can be anywhere here and here. It's inherently probabilistic. It has nothing to do with our measuring tools. They don't have a position until you measure it. Okay, so if you put it all together, we now understand how to think about momentum of such quantum objects, and we now understand how to think about position of such quantum objects as well. And now let's put these two together to build the uncertainty principles ourselves. So Feynman, what do we do next? Feynman asks, Mahesh, can you imagine an electron which has a specific value of momentum? And I'm like, yeah, if it has a specific value of momentum, it's moving at a constant velocity. I'm imagining it like this. And Feynman is like, no, Mahesh, you're still thinking classically. See, these are quantum objects, right? So if they have a specific value of momentum, they should have a specific value for wavelength. So a better way to imagine this is a wave of a specific wavelength, and this wave would extend all the way to infinity. And I'm like, wait a second. I get that electrons have wavelengths, so we are drawing a wave, but why does it extend to infinity? Why can't I represent it this way? Well, because look, the wavelength here and the wavelength here is different, right? The wavelength over here is infinity actually. But we said that this electron should have one value of wavelength everywhere, which means the electron should look somewhat like this. It should extend all the way to infinity everywhere in the universe. So now think about its momentum. Okay, so since I know its momentum perfectly because it has one specific value of momentum, delta P is 0. There is no uncertainty in momentum. But what about its position? Where will you find this electron if you were to measure it? Well, for that, the probability, it depends on the amplitude squared, but look, now the amplitude is the same everywhere, which means the probability of finding this electron is the same anywhere in the universe. In other words, the uncertainty in finding this electron is infinity because I can find it anywhere in the universe. This is the key that Feynman says. Yes, this is nonsensical, but if you try to create a quantum object which has one value of momentum so that there is no uncertainty, look, you inevitably end up with having infinite uncertainty in its position. Not because you don't know its position. No. Now, the probability of finding that electron is the same anywhere. That's why the uncertainty goes haywire and becomes infinity, right? Now, let's try to think about a more realistic quantum object. So we need to localize it a little bit more. I need to narrow down its position, which means I have to decrease its uncertainty. How do I do that? Well, again, think about it. If I have to narrow it down, I have to make sure the waves have zero amplitude at some places. How do you do that? Well, Feynman says just add more waves to it with slightly different wavelength. Wait, why? What does that do? Well, because it has slightly different wavelength, there are certain locations where the waves of the peaks and the valleys will line up over here. In these places, the amplitude will be much higher. But there will be also other places where the peaks and the valleys line up like this. In such cases, they will destroy each other, destructive interference. And when we do that, we'll now end up with a new wave that kind of sort of looks like this. I know it looks ugly, but look what we have done. Because now there are places where the amplitude is very high and other places where the amplitude is low, I have narrowed it down. So this is much better than before when it comes to position, but it comes at a cost. You see, because to narrow down the position, I had to add two waves of two different wavelengths. That means now this object has two values for momentum. What does that mean? That means if you are to now measure this particular electron's momentum, there's a 50-50% chance of having it to be either one of them. In other words, narrowing down the position, decreasing the uncertainty in the position automatically has now increased the uncertainty in momentum. It's no longer zero. You can see right in front of your eyes, it has nothing to do with measurement. That's how the quantum objects work. And if you want to narrow it down even further when it comes to position, you add even more waves. You can do that. But if you add more waves, you're going to increase the uncertainty in the momentum even further. Decreasing one increases the other. Beautiful, isn't it? And by the way, I know these are ugly drawings. So here's an Audacity simulation over here. If I add two waves of slightly different wavelength, look, I can destructively interfere them so that I can narrow down the positions. High probability of finding the electrons here. But if I add even more waves, see, I'm narrowing it down even further. In the limiting case, I can add so many waves of different wavelengths such that I will get one specific location where there's a high amplitude and almost zero amplitude everywhere else. Now, this is a highly localized electron. The probability of finding the electron is super high in this region. That means the uncertainty has gone down dramatically. But because I've added so many waves of different wavelength, it has so many values of momenta, that means its uncertainty in the momentum has gone up. So this is it. This is the uncertainty principle. Nothing to do with the measurement, nothing to do with our instruments, but inherently how quantum objects work. Just think about this. Try to create a quantum object in your head which has a perfect value for momentum and a perfect value for position. It's not possible. Okay. And that's the uncertainty principle. That's why if you take their product, it should have a minimum value, Heisenberg said, and that minimum value happens to be h divided by 4 pi. We can derive this as well intuitively, which we'll probably do in a separate video, but at least we got the essence of it, right? Finally, Feynman, how does the uncertainty principle stabilize the atom? Well, if you go back to the classical model of the atom where the electron is going around the proton, say in the hydrogen atom, then this cannot work because the electrons are charged particles. So charged particles, when they accelerate, they should lose energy to radiation, which means as it loses energy, it should plummet into the proton. But that doesn't happen. Why? Nobody had a real answer for this. But Heisenberg's uncertainty principle can help us understand why that cannot happen. Well, the simple answer is electrons are not simple particles. They are quantum objects. So think about it this way. The uncertainty in the position of the electron is pretty much the size of the atom, right? If the atom is so big, we know the electron has to be somewhere over here and not somewhere over here. So there's a high chance of finding the electron over here. So its uncertainty is over here. Now, if the electron were to plummet towards the nucleus, towards the proton, then its uncertainty would reduce. And if the uncertainty in the position becomes very small, its uncertainty in the momentum would become very large, meaning the electron would now have much larger velocity, which could actually propel it outwards. And that's why, because of that undefined very large momentum, it will not be able to it will not actually fall into the nucleus. It will come right back up. So the uncertainty principle ensures electrons do not lose energy and fall into the nucleus. It's the principle because of which electron has to be having some energy and stay away from the nucleus. And that's the reason why today we think of it in terms of an electron cloud. The uncertainty principle saves the atom, it stabilizes the atom and allows everything to exist, including you and me. So what do you think about this? Do you think you now have a much better intuition for the uncertainty principle and much better appreciation for it as well? If you did, let me know. And yeah, stay tuned and subscribe if you want more quantum mechanics stuff. It's coming soon. See you.